together, right? Then we will use the P series test to check the our choice of series sigma Bn is convergent convergent or divergent. If sigma Bn is convergent, then sigma n is convergent. If sigma Bn is divergent, then sigma n is divergent. So this is that's it for the limit comparison test and P series test. So next, if I move to the next method, then the next method is how to check the convergence of an alternate series. If we look at the PPT, then an alternated series is a series whose terms are alternatively positive and negative. Okay, here I have put two examples, that 1 minus 1 half plus 1 by 3 minus 1 by 4 plus up to plus is sigma n is equal to 1 to infinite minus 1 raised to n minus 1, and nth term is 1 upon n. Okay, 1 upon 2, 1 upon 3, 1 upon 4, like that. And the second is minus 1 upon 2 plus 2 by 3 minus 3 by 4 plus 4 by 5 is sigma n is equal to 1 to infinite minus 1 raised to n upon n plus 1. So these both series are alternating series as all the terms are alternatively positive and negative. Okay, so here minus 1 raised to n minus 1 or minus 1 raised to n terms is just to indicate the sign that in this series all terms are coming alternatively positive and negative. And to decide the convergence of the alternate series, we will take the Leibniz test, the alternating series test, or we can say that it is Leibniz test to solve to check the convergence of alternate series. If the alternate series sigma n is equal to 1 to infinite minus 1 raised to n minus 1 into Bn is equal to B1 minus B2 plus B3 minus B4 plus B5 minus B6 plus up to plus all terms Bn is greater than 0. If this alternate series satisfied the two conditions, then the series is convergent. The first condition is Bn plus 1 is less than or equal to Bn for all n. That means the series is continuously decreasing. Okay, so Bn plus 1 less than or equal to Bn for all n. And the second condition is limit n tends to infinite, Bn is equal to 0. Then the series is convergent. So if these two conditions satisfies, then we can say that from the Leibniz test the given alternate series is convergent. If one of these two condition is not solved, then we will say that the given series is divergent. Okay, so let us look at one more example about how to solve the alternate series. But before we take the example of alternate series combinedly, I will take the one example of absolutely convergent series and conditionally convergent series. So first we will take the definition of alternate series, conditionally convergent series and absolutely convergent series. So this is the definition of the absolutely convergent series. If a series sigma n for whom sigma modulus n, that means the absolute series of sigma n, is convergent, then sigma n is called absolutely convergent series. So if we want to prove that the given series is absolutely convergent, then we need to prove that sigma modulus of n is convergent. So this is absolutely convergent. But if sigma n is convergent but sigma modulus of n is divergent, then we will say that the given series is conditionally convergent series, which we can see in the PPT for the conditionally convergent. A series sigma n is called conditionally convergent if it is convergent but not convergent absolutely. That means sigma n is convergent but sigma modulus of n is divergent. Okay, so this is mainly asked for the alternate series, because for the alternate series all the terms are alternatively positive and negative. then if when we take the absolute series, then all terms are positive, then we need to check the convergence of that absolute series again, and if the absolute series is convergent, then the alternate series is absolutely convergent. If the absolute series is divergent, then main alternate series is conditionally convergent series. Let us look at one example for to check the conditionally convergent or absolutely convergent. So let one more example here, so that an alternate series sigma n is equal to 1 to infinite minus 1 raised to n minus 1 upon n is equal to 1 minus 1 by 2 plus 1 by 3 minus 1 by 4 plus up to plus is conditionally convergent. We need to prove that this series is conditionally convergent. So what we need to prove? We need to prove that this alternate series is convergent. But if we take the absolute series of this part, when we take the absolute is that modulus of n, if we take the modulus of this part, then the series remains, this part will equal to 1, and the remains part is sigma 1 upon n. So this series is we need to prove that this series is convergent, but the absolute series of this is divergent. Okay, so after all, this series will be conditionally convergent. So first we will prove that this alternate series is convergent. So here this is the alternate series with here an is equal to 1 upon n. So implies an plus 1 is equal to 1 upon n plus 1, and an plus 1 is less than an for every n. Okay, so an plus 1 is less than an for every n. So this is first condition for the Leibniz test. Okay, and the second condition is limit n tends to infinite, an is equal to limit n tends to infinite 1 upon n is equal to 0. So both conditions, that limit n tends to infinite, an is equal to 0, and an plus 1 less than an for every n. So these two conditions for the checking the convergence of alternate series by Leibniz test. So by the Leibniz test, this is our condition number 1 and this is our condition number 2. So by Leibniz test we can say that the given alternate series is convergent, right? This series is convergent by Leibniz test. Okay, by Leibniz test the given series is convergent, but in this example we need to prove that this series is conditionally convergent. So now we need to prove that the given series is the absolute series for the given series is divergent. And as I told you, if we take the absolute series, then absolute series sigma modulus of n is equal to sigma modulus of minus 1 raised to n minus 1 into 1 upon n is equal to sigma 1 upon n, right? And this series is divergent. Why divergent? Because this is 1 upon n raised to p type series. Here 1 upon n raised to p. Here n raised to nothing but 1. So here as p is equal to 1, and we know that the p series test is convergent. 1 of sigma 1 upon n raised to p is convergent if p is greater than 1, and the series is divergent if p less than or equal to 1. So here p is equal to 1. So this series is divergent, okay, by p series test. Okay, so this series is divergent. Here alternate series is convergent, absolute series is divergent. Alternate series is convergent, but the absolute series for that alternate series is divergent. So after all, the alternate series is conditionally convergent series, not absolutely convergent, because absolute series is divergent. So we can say that sigma minus 1 raised to n minus 1 into 1 upon s is conditionally convergent series. So this is for the alternate series. We can look at this theorem that if a series sigma n is absolutely convergent, then automatically that is convergent. Okay. Now quickly move to the ratio test. This is D'Alembert ratio test, which is next very most important method. The statement of this D'Alembert test is if limit n tends to infinite, modulus of n plus 1 upon n is equal to n, and if L less than 1, then the series is absolutely convergent, that means convergent, and if L is greater than 1, then the series is divergent, and if L is equal to 1, that means limit n tends to infinite in modulus n plus 1 upon n is equal to 1, then this test is inconclusive. That means we cannot say that the series is convergent or divergent using this test. So we need to clear that when we are going to use the ratio test, at that time we have to clear that if L is equal to 1, then all the work done by us will going waste, and we need to solve the example using another method. Okay, so if L is less than 1, then it is okay. L is less than 1, series is convergent. L is greater than 1, the series is divergent. So let us let's take one example to using this method, how to solve. Okay, check the convergence of the series sigma 2 raised to n minus 1 upon 3 raised to n. This example in GTU January 2010. Okay, so it is clear that here an is equal to 2 raised to n minus 1 upon 3 raised to n, and if we take n plus 1, then n plus 1 is equal to 2 raised to n plus 1 minus 1 upon 3 raised to n plus 1 is equal to 2 raised to n into 2 minus 1 upon 3 raised to n into 3. Okay, and if we take 2 raised to n common, then 2 raised to n 2 minus 1 upon 2 raised to n upon 3 raised to n into 3. Okay, and then if we take limit n tends to infinite, n plus 1 upon n, then is equal to limit n tends to infinite in modulus 2 raised to n 2 minus 1 upon 2 raised to n upon 3 raised to n into 3 multiply by 3 raised to n upon 2 raised to n into 1 minus 1 upon 2 raised to n, and after all it is equal to 1 by 3 limit n tends to infinite in modulus 2 minus 1 upon 2 raised to n upon 1 minus 1 upon 2 raised to n. So after all this part is 0, this part is 0, so this answer will be 2 minus 0 upon 1 minus 0 is equal to 2. So after all answer is 2 by 3, and 2 by 3 is strictly less than 1. So by D'Alembert test, if L is, this is our L, if L is less than 1, in condition number 1, that if L is less than 1 then the series is convergent. So by D'Alembert test, the given series is convergent. Okay, so using D'Alembert test we can say that the given series is convergent or not. So this is for the D'Alembert test. In the same way, if L is greater than 1 then the series is divergent. Let's look at the last test, which is Cauchy's root test, which is just going in the same way as the D'Alembert test. If the limit n tends to infinite, nth root of modulus of n is equal to L, and if L is less than 1 the series is convergent, L is greater than 1 then the series is divergent. If L is equal to 1 then we cannot say anything about the convergence of the series. In the same way as D'Alembert test, we just change in this test is, here we need to take the nth root of modulus of n, and in D'Alembert there is n plus 1 upon n. So that is it for today. These are most important method in convergence of series. So please try to solve more example related to this method. Okay, thank you very much. Thank you.